One of the primary client objectives in the design of a residential building is to maximize the views from it. Within real estate development, especially in New York City, better views can dramatically increase the value of a new building. However, in dense urban environments, desirable views are increasingly limited and challenging to detect without the use of aerial drone photography, which is limited in its application as it is taken from a single point rather than each window and is not quantifiable. In response to these challenges, we propose a 3D framework that allows for the identification and exploration of building designs according to 4 different types of view analysis. This data-driven approach allows architects to quickly iterate building massing options with high view performance to meet client expectations. This is accomplished through a topology-based approach for design classification, which allows architects to consider a wide variety of building forms and work within practical workflow time constraints. The 3D analysis framework and catalog allows the user to pick from a range of geometric operations, such as extrude, loft, and fillet, for design optimization relative to view. It gives the users the ability to weight the relative value of 4 different view types of view analysis based on subjective preference. Lets the user explore high-performing options through filtering of metrics with the ability to save specific building forms for future comparison, allows the user to export selected forms with associated view data for development in other software, and finally allows the user to import building forms from other modeling software for view analysis and comparison with saved forms. We will next demonstrate the capacity of the framework through a typical architectural workflow. An architect first selects the spatial features that will be used to generate the parameter space, such as a lofted form with 3 massing blocks that can scale non-uniformly. Next, the user can weight the relative importance of the different view types into a combined view score, for example, 40% unobstructed, 40% landscape, 20% building variation. Unobstructed is the average distance from a window to obstructions within a human field of view. Landscape is the view to desirable landscapes such as rivers or parks. This analysis can reveal how certain landscapes are visible or not. For example, Battery Park, which intuitively might be assumed to be visible based on its proximity to the selected site, is not actually visible. Building variation measures the diversity in building age as a proxy for how varied the visual character of the buildings in the view are, as those typically correlate with the year built. In this example, the building variation analysis reveals unexpected diverse views low down in the building. Landmark is the view to selected landmarks such as the Empire State Building or the Brooklyn Bridge. Once these preferences are set, we can compute the design catalog. The design catalog is obtained by exploring the topology of the view function, which is the combined view score defined on the high-dimensional parameter space that represents the possible design variations. In particular, the set of maxima of the view function form the design variations that make up the catalog. By using this method of populating the catalog, the designer can explore and compare only distinct design variations, rather than large sets of extremely similar designs. The design catalog is explored by using parallel graph chart to filter for user criteria, such as specific view type, or floor plate efficiency, or the viability of each floor plate based on the ability to fit the elevator core. Once the user has isolated a set of designs they like, the designs can be saved for future comparison. Our 3D framework also allows for the filtering of specific windows within a single building. The perspective from any window can be shown, adding a qualitative evaluation aspect to the quantification of the view. Additionally, for the selected windows, the buildings that are visible can be highlighted. This can be used to isolate areas with view limitations or view opportunities that can inform future design refinement and the marketing of the building. The process of selecting spatial features and combined view score weighting can then be repeated to generate another set of high-performing building forms. These can be saved and compared against the previously saved designs. This allows the designer and the client to easily understand the view possibilities for the site relative to the design intent. Once 1 or 2 design massings have been selected, they can be exported as a mesh and a CSV file with associated view data for each window. The designer can then import the mesh and CSV file into a modeling software they are familiar with for calibration relative to other constraints, such as structure, environmental performance, program, and zoning. Once the design is elaborated, it can be imported back into our 3D framework and the view performance can be compared against the previously saved options. Our 3D framework can perform computational view analysis for iterative design and seamlessly integrate into an architectural design workflow. It achieves this by reducing view analysis computation time, an intuitive user interface which facilitates comparative design exploration, and the ability to exchange geometry and window view data with other software platforms.